Hello viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about designing of battery banks because it's a very big diverse topic, so let's dive deep into it. Now, batteries are becoming very important in our day-to-day life. It's no longer something that, oh, you start a cranking your car or things like that. That's how it started. Now it's like it's the car energy source, and it is also running trains in some places. It's running drills. It's running laptops, mobile, solar, you name it, and everything under the sun is running on batteries. So its day-to-day importance is very high now, and back in the old era, if you understand lithium ion chemistry, if you understood lead acid chemistry, you good. Like there were, of course, there was still difference between anode and cathode construction, materials used, the strength used, and all that. There was always that, because again, the lead acid battery, same chemistry was used in submarine battery that lasted 15 years versus your garbage technology that is available right now that barely lasts 4 or 5 years. So chemistry was the same, but that created an era where we had multiples of, like, 2. So it's like 6 volt. The early batteries were like 6 volt car batteries. Again, you can still see 6 volt batteries used in golf carts. 6 volt, then it upgraded to 12 volt, then it upgraded to 24 volt, and again in home inverters everything was multiple of 12 because we were making so many lead acid batteries. So everything around us was focused on that lead acid kind of voltage. However, that era has gone. So now we have very fine-tuned voltage selections. So 18 volt systems are available now. So you have different voltage and different amp levels. So current requirement has went bonkers, meaning in some scenarios you're like, hey, modern electronics, you barely have to give 0.5 amps maximum to even 0.25 amp, you good, to some things that are like in car cases 400 amps. So amps are going bonkers, and unique cell chemistry to choose from. It's much more different compared to, like, much more diverse in case of lead acid to lithium ion chemistry. In lithium ion, you have a lot of options. For example, lithium iron phosphate, lithium nickel manganese cobalt, lithium titanate oxide. All those things have different voltage curve, different way of behaving, completely different. They're fundamentally different. The only thing they are same is that they are using lithium as charge carrier. So unique cell chemistry to choose from. And these batteries, whenever you are talking about, be it a smartphone battery, be it a power bank battery, be it a batteries, these are tailor made for intended purposes, meaning engineer that is fine tuned and like he knows his stuff when it comes to EV may not be the right person to design a battery for mobile phones, may not be the right person to design a battery for laptop, and vice versa. These are tailor made for intended application. You cannot generalize. They're very tailor made, and it will become clear as the further we dive into each of the vectors that we control. It will start to make far more sense. And operational conditions is the primary vector that you design for, and then lifespan, how long do you expect it? For example, you're like, okay, I'm sending my satellite into, let's say, low earth orbit. Again, what kind of satellite? If it's a military satellite with active propulsion that's supposed to last at least, let's say, 5 years, it's completely different versus same low earth orbit, same outer space environment, versus a CubeSat that if it works only for 5 months, more than good enough. So again, lifespan also plays a role into it. So operational conditions, lifespan, all of these go into the battery selection. It's a very custom job, so to say. It's not a ready-made pant. You have to go to the tailor, get it properly measured, then you have the awesome pants. So this is the battery ecosystem. Now, the first step before you get anything done, this is where you start. You start with cell selection. Cell is the, like, same way, same building block of life. Cell is the building block of basically batteries. And cell is the core of the system, meaning the voltage is always decided by the cell. Meaning it does not matter you have a tiny lithium, lead acid battery that is 2 volt. Does not matter a submarine battery that is still 2 volt. A cell will always have same voltage, and I'm assuming if you've cleared class 8, you know this. So cell voltage does not change by the size, only the capacity change by size. Generally, the bigger the cell, if same chemistry is being talked about, you will have more capacity, more amp power. It will not change in voltage. Voltage is always same, and even the voltage curve is generally always the same in terms of state of charge. So cell is the core of the system. That's how you start. And then you never talk in voltage. Like, again, it, because of we are using lead acid for so long, we are like, okay, just 12 volt and all that. But whenever you are actually talking about lithium ion systems, you have to understand it's never a flat line or never a number. Like, for example, it's like, oh, I'm buying this lithium ion battery, it's like 3.6 volt. That's not good enough. You cannot just say that, like, oh, it's a 3.6 volt system. Again, what C rating? and what is your intended C rating. So if, let's say for example, you are like, hey, I want a small battery pack that can do power delivery charging, 100 watts of charging. Can your lithium ion chemistry support that? Absolutely. Problem is your capacity will shrink and your voltage will drop way too quickly. For example, same chemistry, okay, same chemistry, same cell, I'm discharging it under 1C. Let's say it's a old power bank that barely charges a 15 watt. Voltage goes from like at load, like fully charged battery, I apply load, it drops to basically from 3.6 volt to 3.3 volt, and then you have a flattened curve, and then it almost gets depleted at, let's say, roughly 3.2 volt. Cool, awesome. Same cell chemistry, and you're like, okay, now I'm gonna apply a power delivery circuit to it. Now because again, you're dumping far more watts, the C rating on the cell goes up. Now you have a C rating of 5, high current. And here's the deal, the moment you turn on your load, it goes from 3.6 volt to 3 volts. Basically, if your BMS is designed for the 1C curve, it will trip. It will not even allow it to work. And assuming your BMS is properly rated, now you'll find your voltage drops to way too low, almost 2.98 volts. And it's based on C rating. So that's why curves are the key, not just a number like, oh, the cell goes to 4.2 volt. No, that's the maximum voltage generally they are talking about. Nominal voltage will be different, and again, nominal to you is completely different. For example, a power bank that is designed for again 15 watts, it's a very easy to make, very cheap. But a power bank that is designed to, again, in the same size, because again, you generally have 100 watt hour limit in airlines, so you will never able to increase that. But you want a cell that can give you power delivery of 100 watts up to, yeah, at that point you need high cell capacities, like high current capacities in the cell, and you have to design circuit to manage that, not to freak out, hey, the battery voltage went to 2.98. It should not freak out on that, and you have to accommodate for that. For example, how many cells you have. You may like, hey, 2.98, I do not have enough cells. Okay, increase the number of cells so you have the exact voltage under load. Let that be very clear. Under load, you do not want to create a undervolt scenario. It's like, hey, I put a load, the voltage dropped too much. For example, in power delivery, you may require 20 volt at 5 amps for 100 watts, and you're like, okay, the cells are again, because voltage dropped so much, and you had the cell count for 1C, you're like, oh, that 20 volt is now dropped to 18 volt or maybe even 15 volt. That is unsafe territory, unsafe for the equipment. Equipment most likely will shut down. It's like, bro, this is not right. So that's why you never talk about voltage, you always talk about the curve. And if you're talking about like some engineers, you will always say, hey, look, I'm looking for this cell. What is the 2C rating of this? Again, you will figure out what is the C rating that you need, and based on that, you will look into the curve. And again, if you want something like very short lived, you will focus on this area. You want a cell that is like very long lived, you will focus on this area. The reason is that if you have extra cell to make sure the voltage never goes very low, you get the advantage that voltage never gets too low. So discharge cycles, like basically how much you can utilize, goes up. But again, you can do cost cutting also, and then again, that may be desired from a planned obsolescence point of view. Like, hey, let's focus on this area, not in this area. If you focus on this area, you're like, hey, let's put, let's say, 5 cell. You're like, we can get around with 4. Yeah, that is true, but it's just like after 6 months, you'll find, hey, my power bank no longer holds enough charge. So again, curves, not voltage, curves, voltage curves. And voltage is not static. This is another aspect. Because the voltage is changing so much, you have to accommodate for it. Now, thankfully, most circuits are designed for that. For example, if you buy a drone motor driver, it's never like, oh, it's a 12 volt system. It's never that. It may say that for our convenience, but if you read the spec sheet, it will always say I can go as low as, let's say, 10 volt, as high as 15 volts. It will always say that. And you, again, if you already have the equipment, you have to design your battery bank so the full charge and fully discharge never goes above that. And some scenario, you may even have something of a small shunt resistor to just make sure that you taper off this voltage if you are going too high. Again, that's rarely done, but it could be done, because the moment you put load, voltage drops. So you may have like, oh, it's a 58 volt in a 48 volt circuit. It's just like, yeah, put a little bit of load and it just drops to 48 volt. May require a bit of tolerance. Basically, you do not want a 50 volt rated capacitor in those scenarios. You may want 60 volt rated capacitor. So again, voltage is not static. It's always high to low. You have to design the range. And again, if you design it for, let's say, 50% state of charge, equipment is good, it's cheap to manufacture, easy to sell, low cost, and then it will have very low lifespan. You are making a car, do not do that, because people will remember. Car is expensive. People will remember you and they'll fire a missile up your ass. So voltage is never static. You have to take in the curve under load. And amp hour is defined by total capacity, basically how much oomph it has. Now here's the deal. How do you know that? Well, generally industry has agreed to 1C rating, meaning if you are saying it has a 2 amp hour, what does that mean? That simply means if you drain 2 amps, you should be able to drain it from, like, fully charged to fully discharged, safe voltage, safe voltage of fully charged, safe voltage of fully discharged, till 2 amps for 1 hour. Now what does that mean? That simply means if you're draining less, you can actually get more capacity. Yes, generally everything is standardized to 1C, and if you draw it like 0.5C, you will get a little bit more, but let the refrigerator is a little bit more. It's like 2800 milliamp hour cell will act like 2950 milliamp hour. So that's why they generally say the nominal rating. Yeah, they are expecting you to put some load on it. So again, it's a very good scenario where you're like, hey, what if I have a very big cell and very low current? You will be shocked how long it can last, simply because it's like, hey, from that C rating, the capacity is much larger. And again, the voltage drop will also be less. So you'll have much flatter time. Is there. Now, every cell chemistry, basically lithium iron phosphate, lithium titanate oxide, nickel manganese oxides, all of those things, they have different curve. Their curves will be different. Whenever you are buying a cell, even 18650, even if all of them are nickel manganese, each brand is completely different. The special sauce they are putting into it is completely different. You'll find that Samsungs are kind of well known for oomph. They have, like, they can sustain 10 10 C, 10 oomph. The oomph is very high. So generally people who are making drill batteries, they will focus on that. And then you will find, hey, people who are making laptop batteries, they are focusing on LG chemistry. Why? LG chemistries are generally known for a bit more capacity, but they cannot go oomph. Now they're like, why it's okay for drill to not have that much capacity? Well, you're not expected to have a drill going, I'm doing this for 4 hours. It's only and again, the voltage will dip, but it will also bounce back. So if you design its circuitry correctly, it will bounce back when you're like, oh, done. It bounces back to the safe level. So all of these things have to be taken into account when you are selecting the cell chemistry, even into the same umbrella. And geometry also plays a role now. Like, really, from cooling point of view, absolutely. From other points of view, like generally prismatic cells have different kind of characteristics versus cylindrical cell. So 18650, you will like, okay, 18 is the diameter, 65 is the length. What the hell is 0? 0 means cylindrical cell. So that's why 18650. So each geometry has a different kind of characteristics. Cylindrical cell fundamentally has different geometry of charge flow, different internal resistance compared to prismatic. Prismatics generally have better internal resistance characteristics. So if you want something that can dump a very high surge current, you will generally focus on not cylindrical, but prismatic designs. Again, internal geometry could be completely different. You may have a, like, tabless design that Elon Musk was championing to solve that issue. You have to pay attention to that. Geometry and chemistry, all of them will play the role into it. Now you will hear this term C rating. Every graph has the C rating. What the hell that means? That's a very simple thing. C is X multiplied by amp hour. So whenever you say 5C is capacity, what does that mean? X is the battery capacity in amp hour multiplied by 5. So 5C simply means, oh, the battery is, let's say, 10 multiplied by 5, that means 50, meaning you should be able to drain 50 safely. Now, not for 1 hour, of course, but for 50 amps, it should be like, I am safe, I should not overheat within the temperature. Again, they will never give you, this sort of temperatures are always standardized to 25 degrees Celsius. I have no idea why. And again, if you are designing anything for India, please look into the graph, because again, India is hot. Focus on 50 degrees Celsius graph. So they will say at 50 degrees C ambient temperature, yeah, it goes down to, let's say, again, 5C rating will go down to, let's say, 3.2C. So again, if you are designing something for India and you do not want it to catch fire on in India, you design for that. That's why if you're like, hey, I bought it from Netherlands and it catch fires in India. Yeah. C rating is just amp hour multiplied by that C number. And again, you may find prismatic cells have very high, like, 20 C. It's like, damn, it's almost like a capacitor at that point. So now another aspect is, that's the oomph it can give, but that oomph is not efficient. For example, 1C, everything is tailor-made for that 1C rating. So, oh, it's a 10 amp hour battery. That means at 1C, it's 10 hour. What does that mean at 20C? It's like, doesn't it still means it gives you the same watt hour? No. The watt hour will go down. So if you're like, hey, 1C loading gives me this, you're like, what about 2C? Yeah, your capacity goes down drastically. And you're like, what about 3C? You'll be shocked. So you have a 70 watt hour battery in a laptop and you did not design the C rating correctly. You'll find it's only dying very quickly. It will run. It will give everything it has. but it will run out very quickly. Like, hey, and then you measure the power. It's like, my battery is 70 watt hour. My computer only consumed 30 watt hour and it died. How? Because the C rating was not matched properly. So C rating, you have to match. You have to like, what is the capacity at that C rating? Do not take one C rating and it's like, at 5C. Like, take that 5C capacity rating also. That's why you never look at the voltage or static numbers. You always look at the graphs. Another aspect is there are generally two contradictory factors: safety and capacity. Now, law of physics is very clear. Anything that fundamentally has energy has the ability to dump that energy. You take steam and you're like, to steam, put a lot of power. What happens? Boom. We had steam, locomotives going boom and literally flattening a whole station. Again, same thing goes with lithium ion chemistry. Any lithium ion chemistry that has like a lot of capacity, fundamentally it catches on fire because it has so much energy. And again, as you go into safer chemistry, fundamentally the voltage goes down and you have less capacity. It has higher safety factor. For example, nickel manganese cobalt has like most amount of, it's perfect for your mobile phone because again, even in small volume, you can have a lot of watt hour. Cool, awesome. It catches on fire. But in cars, people are like, yeah, we seesawed, and I'm old enough to know this seesaw. Whereas like, oh, if cars will always choose lithium iron phosphate because it's like, it's safer and all that. Then people are like, no, but we want range because again, Elon Musk jumped into laptop batteries for that system. I'll explain why he jumped that. Then people are like, okay, now electric cars catches on fire. Now people are like, okay, that was the reason why we did not choose it in the first place. So that seesaw happened. And if you're like, hey, I want this thing to I buy it and I forget about it. Okay, use lithium titanate. Just forget about it. So all of this, and lithium titanate literally catches on fire and it burns like wood. It will not boom to the wood. Like, it's not like, oh, short circuit equals kaboom. It was not like it will swell up or something. It just burns like wood. So, but capacity goes down. So you always have to choose between capacity and safety. For mobile phones, for laptops, we always choose capacity because even if it goes boom, it's not too dangerous. That's why aeroplanes only allow 100 watt hour. But when you're talking about cars, we have sunk sea liners with that. So people have learned the hard way that, yeah, let's come back. Let's bring the seesaw back to lithium iron phosphate. It's a bit safer. And cell matching is one of the critical aspect that separates between okay kind of operations to like quality military grade operation. For example, how the heck same cell manufacturer, like let's say Sony as a cell manufacturer, gives the cell and you put it in normal satellites and it only lasts for 1 year. You put the same cells to a company that is specializing in military, and randomly you find, hey, it's working for 5 years. How the hell that happened? Yeah, they did cell matching. And again, any company that gives you long warranty on cells, like in India, there are a lot of new manufacturers coming online. They are still buying cells, but how the heck they are giving you 15 years warranty? Well, they are doing cell matching. What does that mean? That's simply same these curves. It can be plotted in a equipment that puts load on it, different temperature, and logs everything, meaning you can figure out what is the internal resistance. And because it's a chemical engine, all of them are different. All cells are different. Now here's the deal. If you have to make a pack of it, and let's say you put 6 of these puppy into one pack, you will do very well if you match all of them to as close as possible. For example, variance will always be there. A manufacturer will do its best job to have low variance. For example, let's say manufacturer say, hey, our variance from the best cell to worst cell will always be within, let's say, the tolerance of 10%. Cool, awesome. That means if you want to put in military satellite, instead of, let's say you need 20 cell, you will buy 200 cell and you will test all of them. And you're like, wouldn't that compromise some amount of lifespan? Yes, but matching gives so much back that it's like, yeah, it's worth it. You match every cell, you test every cell in a controlled environment, controlled temperature, putting under load and everything. You test it and then you'll find where the cells lie and you group the cells closest to each other. Basically, this cell has, let's say, internal resistance of 10. This cell has 10.1, cool enough. This cell has 9, okay, let's put it different. This cell has 9.8, okay, let's put it in group A. You match it as closely as you can. Then you put BMS, then you put balancer, and then you're like, okay, now this pack can last a very long time. That's why whenever they are manufacturing car batteries, it's always done on the same lot. That's the best they can do. But when you want to like extra careful, like militaries, they're like, yeah, that's not good enough. Actually test every single cell. It does compromise a bit of lifespan, but it gives the pack lifespan so larger that it's like, yeah, it's worth it. So cell matching for lifespan. Again, how the heck same cell company is like, yeah, if we are selling you, we are not going to give you warranty of more than 5 years. Same cell, other company can buy it. It's like, yeah, we're going to upcharge you. Again, they're buying far more and we're going to give you 15-year warranty. It's like, yeah, they're matching the packs. And this is clever technique, but again, does require very fancy equipments to actually because again, it's not just 1C. You have to check at 1C, 2C, 5C, all the expected thing. And you do want to have 1 or 2 cycles. You do not want like, okay, I'm cycling the battery 100 times. You want to make sure that it's done under 10 cycles. So cell matching for long life is the very critical trick, and internal resistance is the for ultimate limit, like how much oomph you can get out of it. Again, inherently chemistry can just burn, so it has more than enough oomph. It's just that how quickly it can dump it. So internal resistance, like how much like short circuit current it can handle, that is generally limited by inter. So that's why you cannot have like 500C. It's like internal. Again, that goes to capacitor. Why? Capacitor is just flat plates, fundamentally speaking. Now, that figures out the cell chemistry part. What about series and parallel? Well, this is the interesting part. Voltage part is very easy. You just how much voltage you need based on the curve, not on just like the pack or nominal. On the curve loading, basically you are designing for 2C or 5C, whatever have you. Voltage of the cell under nominal load of your load, and then you divide it by desirable voltage. For example, these cells go to, let's say, 3 volt under load, and you're like, okay, what is your desired voltage at load? 48 volt. Okay, 48 volt divided by 3. Now again, that will give you a range. That is like, okay, fully charged, it gives you this much range, and fully discharged, it gives you this much. So that's how you figure how much cell you need. That's the easy part. Now, then you will have a choice. Do you use small cell? Do you use big cell? Now, each of them is a pros and cons kind of equation. Now, what Elon Musk did was very clever. Back in the old days, there were this sort of prismatic cell. Yes, these were there, but they were so, proprietary, so rarely mass produced, that if you like a startup company like Elon Musk went to them, it's like, hey, I want to place an order. They're like, yeah, we're not going to talk to you. You do not have billions of dollars. So that's why expensive. So Elon Musk was like, hey, what about 18650? This is 2000 to 2005 kind of era. This was the backbone of laptop industry. So people, he has to just put laptop batteries. Yeah, that was the idea. He knew that Panasonic was mass producing it. He dealt with them. So it's like, okay, Panasonic could actually fulfill the order. It's like, hey, I need 5,000 cells. It's like, okay. Panasonic is like, okay, just give the money, we'll give you that. It's nothing fancy. So he built packs like this. Now, not exactly this pack, but you get the point. And the packs were 74 parallel cells and 6 series. Voltage is not high, capacity is bonkersly high. And again, big cells are simple. Like again, you can see how little contacts you need to have in big cells. Penalty is it's vulnerable, meaning you may only have 1 or 2 blown fuse in each cell, not even in each cell, like in the whole pack, you have 1 or 2 blown fuse done. The whole car says like, nope, I cannot. Even though 90% of the capacity is still there, it's just like, nope. But here, when you have like 74 parallel cell, you can, per unit, you can easily lose 1 or 2 cells and it will not even notice. So in your whole car, even the whole lifespan of, let's say, 10 years, you can easily lose 15-20 cells and nobody will even notice. Heck, even the BMS will not notice. Of course, your capacity will go down a little bit, but nobody will notice. So big cells are simple but vulnerable. And again, the pros and cons list is like a whole PhD thesis on itself. But again, it's there. Big cells have a simpler, they have certain benefits, but they are vulnerable. And small cells, they are redundant, but they are messy. Not only in terms of the wiring and all that, because they did figure out, hey, aluminum plate, not the conductor plate, that's it. And just spot weld fuse wire. They figured that part out, cool. But problem is, it's messy in terms of cooling. Cooling here is far easier compared to cooling like this, where they have to serpentine a very specific type of plastic, almost say, that is conductive enough for thermal transfer to have going serpentine around it to cool it. So you have to balance all that. And another aspect is load balance. How the heck you gonna figure out what happens if packs goes out of balance? Like how much tolerance you want to give. Again, that does not matter in day 1. It does matter on day 10, especially matters for 10 years after. So car manufacturers, they have to pay a lot of attention, and satellites. So they have to figure out what happens at the end of it. Like, what happens if one cell does go bad, which it will happen. Sooner or later, it will happen. If you have 1800 cells in a car, few of them will go poof. So what happens at that point in time? So that lifespan, how long is the expected lifespan? Are you expecting this puppy to run in 15 years in geostationary, or are you expecting this puppy to only last 2 years in low Earth orbit, or like in a car case, or 10 years? And assembly, this is another aspect. There is no point of like, oh, I can make this awesome thing, which again, people used to make, but why it was not awesome? It was not assemblable. It was not mass producible. This was mass producible. That's why Tesla became a Tesla. So that's all of these things. Can you assemble it? Can you make this? Yeah, you can make it. Again, spot welding was a very clever trick. Whoever came up with that, clever. The idea is the fuse wire is the fuse freaking wire. Meaning if one cell, for some reason, let's say its internal resistance drifts too much, it dumps too much current, the fuse wire blows, done, saves. So it's a very inherently safe design. And again, it has resistance. So when the early days, they were cells were popping off, then it was not frying the whole pack. Manufacturing and waterproofing. Now, manufacturing means the whole system, and waterproofing is very critical because there is no off switch on battery. Battery has the chemical energy, and if it was fully charged, it has that chemical energy. It does not disappear. So it's like, what if I disconnect it? There is no disconnect. If it's 800 volt, it is freaking 800 volt. You're not disconnecting battery box itself. There is no, okay, I'm going to disconnect every conductor. That's not happening. All you are doing is removing the power line that is going into the main car. There is a contactor there. But again, what happens inside the contactor, everything is still at main voltage. So if main voltage could be high, let's say 400 volt, 800 volt, 1500 volts, it is still there. So waterproofing is very critical. And I think this is the primary reason why electric cars catches on fire after being flooded. My guess, again, it's my guess, is that once they are actually exposed to corrosive water, so to say, dirty water, because there's a DC, it does have magnetic field, almost electrolyzing. Just because of the giant magnetic field it will create at 800 volt DC constantly. There is no off in it. And that magnetic field slowly etches away. Not on day 1, but day 15 of flooding, it does etch. Again, that's why things are randomly catching on fire after being flooded, not on day 1. But day 50 is like, huh. So again, that's my guess. Nothing else seems to fit why randomly it will catch on fire afterwards, other than the fact that waterproofing is failing because of that high voltage. Not that like if you test it, it will be fine. It's just like test it underwater while it has fully charged scenario. Yeah, even the contactor disconnected, that simply means still that contactor you have 800 volts or 1500 volts. So, yeesh. So series and parallel is your system. Like how many series cells you have defines your voltage. How many parallel cells defines your capacity, how much oomph you have, how much tolerance you want. Like you want big cells for longevity, thermal efficiency and all that. You want small cells if you want high resistance. But again, that simply means you have very poor efficiency if you are needing 74. That's why Elon Musk started with this 1863, small company. Medium company, some amount of success, they upgraded to 2170. Major company with serious success, 4680. Ideally you want this sort of system. But again, there is a compromise where you do not have this big of a cell and you do not have this small of a cell. There is a sweet spot. So load balancing matters a lot. Again, all of this will go into the accountant and they have to give a recommendation. It's like, hey, if you do this, these are the pros, these are the cons. And if you do this, these are the pros, these are the cons. And then the market analysis will tell them, it's like, which route in this condition we can choose. Not easy. Now we come to the management part of it. So far, you just built the damn thing. How the heck you gonna manage it? Well, management requires one good thing is that if you have cells in parallel, meaning the positive to positive, negative to negative, is just like pochang, it balances itself out. Meaning if it's like this and you just short everything to basically parallelize it, this energy from overcharged cell will directly go into the lowest voltage, because again, voltage will try to equalize itself. So voltage from here will travel to here and everything will equalize. So you do not have to worry about. So it's like, how the heck Elon Musk is balancing 70 cells? It's not. It's 70 cells in series requires balancing. 70 cell in parallel, it's one big cell. So self-balancing, that's good. But that means anything that is in series, that like in those scenarios, 6S, that does require balancing. Meaning now you have 6 data leads, not data available, voltage leads that will used for balancing and management. Now BMS, whenever people use BMS, generally is a broader term. But in common parlance, BMS simply means protect the pack. Now how does it protect the pack? Well, it has a capping on over and under, basically. Again, that's why you have to choose the chemistry and BMS for that chemistry. You cannot use BMS that is made for nickel manganese for iron phosphate. It will backfire badly. So what is the over and what is the under limit of the amps and voltage? Meaning if your pack is designed in such a way that it's safely able to do 200 amp hour, not 200 amp hour, like 200 amp of surge, your BMS should be a bit above that. It should be like, hey, 200 is your maximum capacity safely, I will only allow 150. And you have to design everything to be less than that. Everything, like, you know, your motor driver should not pull more than 100. BMS should be the worst case scenario. Let's say the capacitors are aged and they're not like, they're going a bit naughty. It's like, okay, it goes up like 120 years, like, and BMS is like 150. That's my upper limit. And the cells are like, dude, I can take it. And again, that's how you make sure that after aging, after 5 years, after 10 years, you still have a working circuit. Because again, the cells will age. Let's say you have a chemistry of 500 amp hour sustained of surge. you're like, you do not put a BMS. You make sure the cell chemistry is always higher. The cell chemistry is the last thing. You never want to touch it, especially in long run application. You're like, if you want this puppy to work for years, you never push it that hard. So BMS is a protection mechanism. Basically, it never allows amps to exceed voltage. It manages voltage on cell level, meaning if it will cut the power the moment it detects one under voltage cell. It will cut the power if it detects one overcharged cell, one cell. And yes, it means it can break your whole car if one cell goes out of whack. Again, it's painful, but it has to be done in order to not catch on fire. So that's the problem. Now, like, okay, doesn't that mean you can have a scenario where capacity wise, you can have 100 watt hour capacity, and when you are actually using, you are barely getting 30? Yes, that happens when you have drifting. And again, drifting is inherent nature of the cell chemistry itself. That's why cell balancing and matching is so important. If you match it, the drifting will happen slowly, compared to if you do not match it, it will just drift. And okay, BMS gives you the protection for voltage, amps, under and over. Cool, awesome. Now, balancing allows you to safeguard against it, meaning it's like, hey, one cell is overcharged, one cell is undercharged. Dump the energy from over cell to this exact cell. And yes, that simply means it's almost applying communism to all the cells. It's like, hey, series cells, it's like, hey, these cells are overheating, take the energy and dump it into the weak one. So basically, during charging, the cells that are weak cells, they will reach high voltage very quickly. So it takes energy from them, dump it into the healthy cells, basically. And during discharging, it does opposite of that. Basically, healthy cells will discharge very slowly. It takes voltage from them, dumps it into weak one. So BMS does not trip. And again, this not only about BMS, it also allows all cells to be healthy enough where the drifting is not amplified. If you do not balance the cells, the drifting becomes exponentially worse, meaning a pack that could be easily 100, let's say 100 kilowatt hour, it will only give you useful capacity of 50, because again, BMS will keep tripping, because again, some cells will get out of whack. So if you have very well matched cells, and then you have a very good balancing circuitry like this Blackmagic technology. I have made a detailed video. I do understand how capacitive balancer works, but do not ask me how inductive balancer works. That does not even, I do not understand that voodoo magic. But capacitor one, I understand. It just attaches all the capacitor in basically series to cell, and then it parallelizes all of them. So on and it does it very high frequency. So then it balances, dumps the energy. Capacitor basically dumps the energy into the weaker cell. And when you series them all, it attaches to the batteries. When you parallel them, they balance it out, then dumps back. Very clever. Basically, it's a very clever flip-flop mechanism. So it's a very clever system, and it allows all the cells to have equal enough voltage. And balancing keep all of the cell same-ish, meaning over time you do not drift. So 100 kilowatt hour capacity remains 90 kilowatt hour useful capacity, meaning BMS not tripping, and it's like actually useful at 10 years point. So it's a compulsory. The BMS that you see on Amazon and all that, most of them are just BMS. They are just safety circuitries. They are not balancer. And again, when you are talking about cars or any sort of equipment that is costly and expensive, it has to have balancers. Unless you are planning to make a what we call planned obsolescence device like DeWalt, and you're like, hey, we have batteries. That is like so expensive. We should have BMS on that. It has BMS. It does not have balancer. That's why when the two central leads where it's leaching energy for that BMS circuit, it under drains them and then it trips, and it's like, poof, your super expensive battery box is poofed because one cell is drained too low. If they had balancer in that, that will not happen. But again, planned obsolescence will not want that. But again, thankfully in cars, everybody does balancer. And I have no idea why the heck this separation happened where BMS somehow does not include balancer. So that, and again, everything is tailor-made for the voltage and current, because again, you can easily find, 3S, meaning 3 cells in series, that is rated for 10 amps. 3S that is rated for 50 amps, 3S that is rated for 100 amps. Does that mean you're supposed to connect like, 318/650 and have 100 amp? Hell no. They're expecting you are smart. And if you have that kind of, let's say, a spot welder kind of requirement, you're going to have cells that can handle that, or have a lot of cells in parallel so you can distribute the load and get your job done. But that's on you. It's a tailor-made system. You're supposed to have balancer if you want long life. You're supposed to have BMS that is matched properly so it does not put strain. Let that be very clear. If cell can go to 100 amp of surge, you never put a BMS that is like, oh, I'm here. You put BMS that is here. It's like, oh, I will never let more than 50 amps touch you. You always have to do that. Only then you can have lifespan. So this is the management part of it. And yes, in car cases, it becomes tedious AF. In some scenarios, it was so expensive, companies developed wireless protocol inside a battery pack because they had like, hey dude, we are balancing 1500 cells. It's too complicated. Yeah, that has happened. Now we come to the thermal part, which is all cell chemistry have their optimum operating temperature. Now, because I have no idea, Europeans, we have 25 degrees Celsius. Again, it makes no sense in India. So if you are building anything for India, please look into the temperature graph and look how it operates at 50 degrees C, not 25. So operating temperature, again, every cell is rated for 25 degrees Celsius. So it means if you have temperature, again, let's say it's a good chemistry, it will be like, hey, keep me above 20, keep me below 30, I will give you, let's say, 2000 cycle lifespan, and I will give you the maximum capacity I have. What does that mean? That, like, let's say the battery overheats, let's say it goes to 35. Does that mean battery goes poof? No. It simply means it will not give you that many cycles, meaning instead of 2000 healthy cycles, it's only going to give you, let's say, 1500 cycles. Instead of giving you 20 amp hour, it will only give you, let's say, 18 amp hour, or maybe even less. So that's why operational temperature, everything is rated for that optimum temperature, 25 degrees Celsius. Or again, if the chemistry is a bit different, it could be, again, when you are designing your own cell chemistry, you can ask the manufacturers, like, hey, change the sauce for hot environment, and they can make it so that the cell is a bit more warm biased. You will have penalty for that, but it will be healthy in that environment, meaning let's say if the capacity goes down, that's okay, but the 2000 cycle count will remain at higher elevated temperature. It can be done. Again, that's why we have chemistry's options, as I like, select your option. So operating temperature, again, you have to maintain it for cycle life and capacity. Now, cooling matters when you are talking about high C loads, meaning if you are charging like ultra charging, I'm going to charge my car at like 250 kilowatt. Yeah, it needs bonkers amount of cooling. And that's during charging and also during discharging. So if you're like, hey, my car, and people like the idea of, like, having electric cars that can go 0 to 60 under 2 seconds, is like, yeah, that's a lot of amp that your battery is draining. And again, batteries are resistors, they are not capacitors. They do have bit of heating up. If you do not cool them at that point, they will degrade. Now again, if you are lucky, they will just degrade. If you are unlucky, they will catch on fire. So cooling matters a lot, especially if you are having high C. Now again, depending on your design, if you are longevity, you do not have the luxury of cooling the batteries, you will design everything so it never reaches that domain of high C. That's up to you. And every chemistry will have a different kind of tolerance. And you may need to heat the cells also. You're like, okay, why? Well, here's the deal. Let's say you are living in a cold place, let's say Canada, and you take your Tesla and you're just like, okay, the cell is almost fully depleted, 0% storage charge. You put it overnight and you're like, okay, in morning I'm going to fast charge it. You put it, if it dumped to 250 watt hour, yeah, your whole cell will catch on fire instantaneously. Yeah, like, yeah, it's cold. Yeah, that's why. The cell will not behave as supposed to. So you do need to heat the cell. And again, if you really want it quickly, your manufacturer can choose to run hot coolant, or like, if it's a air conditioned system, it will run it as a heat pump. Like my AC is running as a heat pump right now. It will do that, so it can warm up the cell, then dump the power. And you can see that in all charging curve, even on your mobile phone. If it's fully discharged, your fast charger will never go full C on it. It will always like, hey, let's warm you up. So it slowly ramps up. So it's like starts to move the electrolytes. So it's like, okay, let's get it jiggling. Let's start warming up. Once the temperature reaches the optimum point, then it's like, full 250 kilowatt, basically 3C. You can do that. So you do need to heat the cells in winter. Again, that does not make sense in India, but it does make sense in Canada. So that is there. Or you can, again, heating part can be bypassed if you have time. Meaning, if you're like, hey, it's fully winter and the cells are fully depleted, you plug it at night, it can choose to slowly charge it. Meaning, it will barely give 1 amp. Like 1 amp to a car, again, that's not to charge it, it's just to warm it up, just to jiggle it up enough. 1 amp then will slowly ramp to 10 amps. They're like, okay, I'm feeling it. Then to 50 amps, they're like, okay, now the temperature is like, and it's like, I got this. So that can be done. Another aspect, cooling at hot ambient, again, aka needed for India and high C users, and or you can choose a chemistry that can deal with it. For example, going from high energy density to basically safer chemistry does ironically also improve the temperature zone. For example, lithium titanate is freakishly weird, meaning it can handle almost minus 30 degrees Celsius to 70 degrees Celsius, and some of the mix can go minus 50 to plus 70. It has that kind of range. So you can choose that. Like, again, if you are making a, let's say, military vehicle, you do not want the complexity of having a heating or cooling system, you may choose that. Again, penalty would be the capacity would be much lower. Benefit would be, yeah, those chemistries can handle surge like there is not why. You may not even bother to put BMS. You'll just put like a balancer just to make sure. Like, your charging current is like, I'm going to give you 500 kilowatt. It's like, meh. So that can be done. So this is the system that Tesla uses, and this was a system from a bankrupt company. You tell me which company was that? So they were making large prismatic cell, very good current capacity and all that jazz, but they did require a flat plate heat exchanger between each cell to make sure that temperature remains okay-ish, especially when you're like flooring it. So these are the thermal aspects. And again, depending on this serpentine system, I can easily see this working in colder areas. In India, you might not want two cells that are not cooled. So you may want to amplify it. Or you may decide, hey, this is not going to work in India. You may be like, okay, let's go back to this. Again, you have to figure all of these things out. So that's why cell battery pack design is not just like lol. It takes a lot of computation, lot of vectors to be managed. So this was my presentation on basically how the heck you're supposed to make battery chemistry. Hopefully you have battery box. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.